First of all, a big thank you for all of you who stay here at the last session of the last day. So my name is Akshal, I am from Singapore Management University. I am going to present our work called dual formulations for optimizing Dec-POMDP. And this is joint work with Hala Mustafa from UTRC and Logo from UMass Campus. So let me start by describing what is the decentralized POMDP model or decentralized partially observable MDPs. So the Dec-POMDPs, they've emerged in recent years as a standard framework for multi-agent sequential decision making. And Dec-POMDPs are great because they can model uncertainty in the environment. Similarly, they can also model a very general real-world phenomenon called partial observability, both about the underlying world as well as about agents not knowing exactly what other agents are observing in the environment. Right? So there is sort of the decentralization in both partial observability and in execution. Similarly, Dec-POMDPs model long-term behavior, so we can do sequential decision making under all these characteristics. Also, recently there are many applications emerging for Dec-POMDPs, mainly in the field of robotics. So right now we have actually Dec-POMDP models and solution techniques applied in real robots. So that's the SMR2 recently, as well as some older applications to work on sensor networks. And also, obviously, they are very computationally challenging. Solving Dec-POMDPs, trying to run Dec-POMDPs, it's next hard. And that's where our contribution lies. So, main contribution is to develop an efficient approach for optimizing policies which are represented as finite state controllers for general Dec-POMDPs. Alright, so let me first start by describing the Dec-POMDP model. So let's start with the simplest setting. So in the simplest setting, we have the bare minimum two agents. Right? We have agent 1 and agent 2. And they are interacting with our environment, which is discretized into a number of states S. Both the agents, they take an actions, let's say action A and action B, and as a result of their joint action, the word stochastically transitions according to some joint transition function. So that's the important part. Transition function depends upon actions of both the agents. And as a result of this transition and as a result of their joint action, some reward gets accumulated in the bank, or this reward is accumulated for this time step. And the important thing is this reward again depends upon the joint action of all the agents. And again, we sort of assume a very general setting in which we assume that the underlying state S prime is actually not observable to either of the agents. What we assume is that based on the resulting state S prime, a joint observation YZ is generated. But here is the sort of vague part that differentiates Dec-POMDPs from POMDPs. So the whole idea is that even though this joint observation YZ is generated, agent 1 only observes its own global component of observation YZ. Right? So agent 1 observes the Y component of observation, and agent 2 observes the Z component of observation. And that's all the sort of where all the complications in Dec-POMDPs come from, and that's why they are fundamentally more challenging to solve than single agent POMDPs. And once we have this model, our goal is to find policies that maximize the expected future reward over a finite or an infinite horizon. And in this particular talk, I'm going to be focusing on infinite horizon problems with its counting factor, gamma less than 1. Alright, so before I describe how to optimize policies, let me say a few words about how do we represent policies. So again, policies in Dec-POMDPs, they map the complete history of observations to an action. So there is no sort of compact release state for Dec-POMDPs. So that's sort of the unfortunate part. But that is not to discourage us. So what we do is that we actually represent policies for all these agents as a finite state controller. So this is already a well-known sort of way of representing policies in partially observable settings, and this easily extends to Dec-POMDP literature. Again, finite state controllers are great because they have lightweight policy execution. There is no belief tracking involved. Agents simply observe their latest observation and look up their next action in a tabular. And they are highly useful in resource-constrained environments such as in robotics application, in mobile and peer devices. And again, I would show that empirically very concise controllers, they can provide often very good solution quality. So that means that controllers are highly interpretable when you want to interpret resulting policies. Alright, so what are our main contributions? So again, we are not the first one to come up with a math programming formulation for optimizing finite state controllers. So there are previous work which formulate the problem of optimizing controllers as non-linear programs. But the main problem with these previous work is that they are basically based on formulating this problem as a non-convex and non-linear program. So as a result, when you solve these problems, there is no sort of specialized solver. You just throw these problems to a standard NLP solver programming solver. They can get stuck in local optima. There is no quality guarantees. Even given enough time, you cannot, there is no straightforward technique to get to escape out of it. And another big problem is that you would need to specify the controller size in graphic. Right? So, for example, you want to optimize 4 state controllers, 5 state controllers, 10 state controllers. Right? Larger controllers are better, but the optimization problem becomes more and more challenging. So, what should be the right size that is computationally tractable and gives us good solution quality? So, in this context, these are our contributions. First of all, we established very close connections between MDPs and decentralized MOPDPs, and in particular to show that there exists, it's a well-known dual formulation, dual linear programming formulation for MDPs, to show that how it extends in a very nice way to a dual mixed integer programming formulation for deterministic finite state controller optimization. Right? So once we have this very nice sort of hold-on tractability for Dec-POMDPs, we can then apply all these nice approximate linear programming and all these sort of nice value function approximation-based techniques for Dec-POMDPs. And again, since we have an MIP formulations, we can get quality counts on optimizing controllers, and we can also show that empirically we get QMP optimal controllers for several of these problems, and also given sufficient time, MIP solvers can avoid local optima. So again, this doesn't have all these problems with MIP controllers. And in particular, we also show that dual formulation is not only useful for optimizing deterministic controllers, but also we can optimize stochastic controllers by using the same or by using a very similar dual formulation. So this dual perspective on decentralized and partially observable planning is very useful. And finally, we also provide some heuristics that describe how to grow controllers so that we can actually get good solution quality without needing to specify a priori what should be the controller size. Right, so let me describe the whole content of the talk in the light of these contributions. This is again a toy example, the roots of which lie in the single agent tiger problem. So again in this problem we assume that there are 2 agents and there are 2 doors, and behind one door there is a tiger, behind another door there is a hide wall. And sort of like cutting the whole story short, both these agents they cannot observe behind which door the reward is. So their goal is to sense the right door at the right time and open the door which has the reward at the same time. Right? If they are not coordinated, then they would get a large penalty. So that's the whole decentralized coordination. Again, how do we represent controllers for this problem? So controller is nothing but a directed graph. So it's a bunch of nodes and a bunch of edges, and a controller can be directed. Right? It's not a cyclic graph. And nodes of these controllers they correspond to actions. So in this case, L stands for listen action. Open right stands for OR, and open OL stands for open left. So nodes correspond to actions, and edges they are labeled by observations. And edges basically tell the controller or tell the agent which controller node to transition to depending on receiving a particular observation. And here are the 2 main problems which we want to optimize over. First of all, for a fixed size finite state controller, we want to find the best action mapping. So phi function maps the controller node to action, and we want to find out the best controller node transition mapping. Right? So that's the main optimization problem we solve. The second sort of additional problem is that how do we increase the fixed size controller so that we can actually get a better approximation of optimal cost. Right? So okay, let me switch gears for now. Right? Let me talk about MDPs. So this is again, I think yesterday also there was a talk where this dual linear program for MDP. So it's textbook sort of material. Everyone knows it. So here it's an MDP with state S, current state S. You take an action A, and the result is state S prime, which is given by the transition function for an MDP. And this is the linear program, and if you solve this linear program, you will get optimal policy for an MDP. It's again a well-known sort of thing. So here, the X variables, they denote, so they are for occupancy measures. Right? We are optimizing over occupancy measures, and X of SA, it means that what is the total discounted amount of time the system is in state S, and action A is taken. So these are occupancy measures, and when you maximize over these occupancy measures, subject to this sort of flow constraints, you get your optimal solution. Right? Standard material. So here is the main idea for our work. Similar in being to dual program for MDPs, how can we develop a dual program for decentralized MDPs? Right, so here is this observation. Can we actually adapt our MDP, single agent MDP dual program, to form a dual program to optimize FSCs? And we show that it can be done. Right? So the first thing is that, so again this is also a goal like, we can actually write a cross product MDP for a POMDP as well as a decentralized POMDP. Now to explain what this cross product MDP is, roughly speaking, this cross product MDP is defined over the joint controller state and the word state. Right? I will describe what the structure is. And since we have a cross product MDP, which is also an MDP, so we can simply write the dual program for the CP-MDP. That's not too hard to do. Right? But the whole idea is that if you just solve this CP-MDP dual program, you would actually get a policy that is not executable in a partially observable setting, because the policy would depend upon underlying state, which violates our Dec-POMDP assumption, as well as the policy would depend upon what this other agent is observing, which violates our decentralized or what decentralized execution assumption. Right? So that's where our main contributions come in. What we do is that we actually add some constraints to this dual program for CP-MDP such that the resulting policy is a valid Dec-POMDP policy. Right? So what a valid policy is? A valid policy is a policy that could only depend upon the local observation each agent has. That wouldn't depend upon the underlying state, that wouldn't depend upon what the other agent in the system are doing. Right? Again, this is sort of easier said than done. There are several challenges when we're trying to find our value constraint. Some of the challenges are that the CP-MDP has an exponential action space. So I will describe why this is so. Right? So again, we have to be smart when we're writing a dual program for CP-MDPs. Similarly, what exactly are the constraints that would define valid policy? That's also not clear. Right? What should be those constraints? So here is the main idea. So here is, let me start by describing the cross product MDP. So on the right hand side, you can see the CP-MDP for two agent problems. So why is it a cross product MDP? Because it's a cross product of controller state of agent 1, that is denoted by P, controller state of agent 2, that is denoted by Q, and the underlying state S. Right? So that's why it's a cross product MDP. Domain actions. So domain actions are A and B. So that's our model actions. The actions of agent 1 are denoted by A, agent 2 are denoted by B. But in addition, what we have to do is that we have to also include controller transitions as an action. That's sort of the tricky part. Right? There are actually exponentially many actions which encode this controller transition function. Right? So in fact, if you count the total number of controller transition actions, they are exponential with the number of observations. So if you blindly write like a dual linear program for this MDP, it's going to go up. Right? So what we do is that this dual linear program has a lot of structure, it has a lot of conditional independencies. So we exploit this independence into our dual linear program by marginalizing out a lot of big occupancy measures, which depend upon all the exponential number of variables. Alright? So here is the final dual MIP. I'm not going to describe in detail, but I will just describe the correspondence of this dual MIP for Dec-POMDPs with that of dual linear program for single agent MDPs. So the first two things exactly correspond to the objective function of the dual MDP. Objective function of the single agent MDP. The objective function is just the expected reward. The first constraint is exactly the analog of flow constraint for single agent MDPs adapted to Dec-POMDPs. And then we have here additional constraints which sort of guarantee that when you have these additional constraints, you will get a very Dec-POMDP. Let me not describe, for example, the last two constraints are the one which sort of enforce this sort of validity in partially observable and decentralized setting. And let me not describe mathematically what they mean, but let me give you an intuition. Right? So in English, what these constraints mean is that whenever the control, let's pick an agent, let's pick a favorite agent, right? Let's pick agent 1. So whenever the agent observes its controller is in state N, then you should make sure that it always executes action A star. A star can be, for example, the actual policy. Right? So if you see the statement, in this statement, the policy or the action A star, its execution doesn't depend on underlying state S or the state of other agent's control. Right? And it may look weird for now, but it's actually very easy to enforce, or it's sort of easy to sort of write in terms of these occupancy measures. So if I say x of n, the total discounted amount of time agent 1's controller is in state n, it is equal to x of n A star, then it sort of implies what I just wrote in English. And that's sort of the whole idea, like how we can add additional constraints so that we have the very Dec-POMDP policy. But again, this is not as straightforward as it looks, because A star itself is a known. We don't know what A star should be. So we have to enforce the simple condition, y number of indirect linear equations or linear constraints can be required. Alright, so let me, again, so that was the dual MIP for deterministic controller optimization. So here is another sort of interesting fact. We can also optimize stochastic controllers using the very similar dual formulation. And we show that instead of doing, so when you optimize stochastic controller, it is typically is used using probabilistic inference. And this probabilistic inference typically involves forward backward message passing like in HMMs on this very large deviance. The size of this deviant depends upon discounting factor. Typically size is like 100 times step or 200 times step. So instead of doing this very expensive computationally challenging message passing, you can just solve this simple dual linear program. So why I call it dual? Because we also use these X variables or frequency measures. And we can show that once we solve this dual linear programs, its output can be used to optimize stochastic effects. Right? So that's why actually dual perspective is a useful thing to have for planning under partial observability. Alright, so again I will not talk about how do we add nodes to the controller, so more details are in the paper. But let me tell you about experiments. So we experimented on all existing 7 or 8 standard benchmarks. So these are publicly available. We compare against previous best finite state controller solvers. So one is the periodic state controller by Pajaran et al. In 2011, and also against standard nonlinear programming approach. And again, our main observations through our experiments was that we actually were able to achieve similar or better solution quality as the previous best solver. But I would say that it's more than an order of magnitude faster. Right? And also we would show that our approach provides provably reactive controllers for all existing problems. And all these resulting controllers are highly compact, so which means that you can easily interpret what the policy is saying. So here are the results. So dual MIP is in red, and y-axis shows the normalized solution quality. So 1 is the solution quality given to the best of all 4 approaches. And on the x-axis you have different instances. And you can see that the red colored sort of bar of the dual MIP, it's basically getting the best solution quality for all the instances. I mean, there are some slight sort of dips, but it's not very significant. And here is the major speed up. Right? So on the x-axis again, we have instances, y-axis is runtime in seconds, and that's in log scale. So you can see that actually dual MIP is able to solve all the instances in less than 1 minute. Right? Whereas other approaches, they take like 10,000 seconds, 3,000 seconds. So it's actually huge speed ups. And we also show that the control, so this is the resulting controller size for different instances. So 3, 3 represents that the controller size of agent 1 is 3, the controller size of agent 2 is also 3. And you can see that only for 3 instances, only for decentralized tiger problem, for box pushing and wireless, we had to add a few nodes to some of these controllers. For all the problems, optimal reactive controller was enough to provide a good solution. So which also implies that final controllers are highly interpretable and compact for all these problems. Again, this is the summary of our work. So we established very close connections between discrete state MDPs and Dec-POMDP controller optimization. And as a result of these connections, we can now actually apply like well-developed theory of linear programming, approximate linear programming from MDPs to partially observable Dec-POMDPs and also in multi-agent circuit. Again, we can get quality counts about local optima, and we can do a whole lot of other things for which you can actually read my paper. With that, I will conclude, and thank you very much for listening.
Questions? Okay, I have a question. When you're looking to generating these loops and placing your programs in a iterative fashion, for example, looking at range pricing and cut.
Yeah. So yeah, I think that's an amazing great observation, and that's what happens when you try to optimize a very large controller size. MIP solvers cannot solve it, right? So in these settings, when you want to optimize larger controller size because they are better, you have to do this standard reward thing, basically column generation, constraint generation. Because ultimately, if you see, these controllers are very sparse. Most of these variables are actually set to 0. So instead of trying C+ to do all the hard work, if you're smart about it, you can definitely optimize much larger controllers, which will definitely improve solution.
Any more questions? So let's take this up.
So I wonder if you can connect what you just said to kind of lifted versus flat representation.
Lifted
versus flat representation.
Right, so I'm not sure about lifted, but I can definitely connect factored representation with that of dual linear programming. So I mean, in Carlos Ustin's thesis or Carlos Ustin's work, he has all these approximate linear programs for factored entities. So I think it's going to be straightforward or relatively straightforward to extend all these approaches to factor Dec-POMDPs, and instead of an LP, but you would have an MIP. So that's going to be sort of the main difference. And that's also, I mean, that's where we are actually also planning to work, or in fact we're working right now on these solving factor representation to approximate MIPs.
Let's thanks to the speaker again.
So this is joint work with Vicente Gomez. So the motivation for this talk or our paper is quite simple. We're combining two existing techniques from reinforcement learning. One is the idea of decomposing tasks into subtasks, so hierarchical reinforcement learning, which allows you to simplify the learning problem and hopefully scale to larger problems. The other formalism we use is kind of maybe a lesser known version of MDPs called linearly solvable MDPs, which have a linear Bellman equation, and as a consequence, learning algorithms tend to be faster for this class of problems. So the idea is simply to combine these two to create hierarchies of LMDPs as opposed to hierarchies of MDPs, which is what typically is done in the literature. So I'm going to briefly introduce these two frameworks. So I'm going to assume that most of you know what MDPs are. So in our case, we are also interested in goal MDPs, or MDPs where there are some states that are terminating. So in this case, you can state the value function without using a discount factor. So as you know, you can state the value function either in terms of state values or action state values. Well, these are non-linear equations because of these max operators that appear in each. And arguably the state-of-the-art learning algorithm, online learning algorithm for reinforcement learning is Q-learning, where you maintain an estimate of the action state action values. You record Q-learning is an off-policy algorithm, so you can record transitions using any policy that you want, and then you apply this update rule, which also has the max in it. So the hierarchical reinforcement learning framework we're going to use is called max Q decomposition, where tasks, well, a single MDP is decomposed into a set of MDPs that correspond to tasks. So these tasks can be organized in a hierarchy. So the leaves of this hierarchy are the primitive actions, and the composite actions can choose between either primitive actions or other composite actions. So the action space of tasks includes subtasks from this same set. And the key idea here is that the value function so what we're going to do is we're going to represent each task as its own MDP with its own value function. So the value function for a task decomposes as a function of the value functions of its subtasks. So that's what we see here. You have to take the maximum over the subtask of this task MI. Okay. So on the other hand, there's this concept called linearly solvable MDPs, which was proposed 10 years ago by Todorov. So in LMDPs, there are no explicit actions. So one interpretation is that there's no explicit actions. So an LMDP has a set of states, of rewards, and a set of transition probabilities from states to next states. So one way to view this is that the system is like a Markov chain that acts on its own. So if you let it be, it will transition between states according to P. So what can we do in a Markov? Well, a Markov chain is uncontrollable. But what we can do in an LMDP is we can choose what the transition probabilities should be. So I can choose any A. So the A here is my control, and I can choose what the next state distribution is going to be. As long as it's consistent with P. I can't choose a non-zero probability of transitioning somewhere where P couldn't transition. So if I choose a non-zero probability, that has to be non-zero for P also. Okay. And it's not for free. So I can't choose the transition probability that I want, because the reward, the immediate reward, depends on a reward that's given by the LMDP, minus a penalty term for diverging from the uncontrolled probability speed. Okay, so KL term, KL is the KL divergence between A that I choose and B that's given in the problem definition. Okay. So you can actually, so what I've described now is one interpretation of LMDPs, so which says that the environment is stochastic and fully controllable because I can choose what the next state distribution is going to be, and the control is a unique control A, which is a probability distribution. So under this interpretation, the transitions look something like this. I'm in a state, I select A, and then I sample the next state from this distribution A. But we can actually take the different views of LMDPs in which the next states that P allow from a state correspond to a set of deterministic actions. So, and in this case, A can be viewed as the stochastic policy over this deterministic action. So under this interpretation, transitions look like this. I'm in a state, I now select this stochastic policy over the deterministic action. Once I decide which action to apply, then that's transition deterministically to the corresponding next state. Okay, so this is actually maybe more, this second interpretation probably makes it easier to think about tasks that we're going to introduce. Okay, so how do you go about solving LMDPs? Well, if you plug this expression for the immediate reward into the Bellman equation, and you do the math, which I'm not going to do here, but you get what you, and you also exponentiate the value function. So Z here is the exponent of the value function, well, divided by this temperature, which determines how the importance of the penalty term. Then the Bellman equation becomes linear in Z. Okay. So, and you can also compute the optimal control easily based on the optimal value function. So one way to solve the one way to solve for Z would be to run the power iteration method, just like you could run value iteration for MDPs. That's not typically very efficient, so Todorov also proposed these online algorithms for LMDPs. So the kind of equivalent of Q-learning is called Z-learning. So Z-learning is this model fee approach to estimating this optimal Z value. So the way Q-learning works is you sample a transition according to P, and you have an update rule that updates the value of Z. So essentially this comes down to doing a random walk in the environment and updating as you go along. So again, this is not a very efficient way to explore, right? Doing a random walk might never get you to where you're going. So Todorov also suggested this another update rule based on importance sampling. So instead of sampling using which is the random walk, you instead sample using your current estimate of the optimal control. And then you modify the update rule by tagging this correction term in the end, where the correction accounts for the difference between the sample policy A, well A hat, and the real transition probabilities P. Okay. So this is the difference between Z-learning and importance sampling is that to compute this correction weight you need access to P. So that's a slightly limiting assumption, but in fact P can be very simple. In our experiments we just use uniform probabilities. So that case we do have easy access to P. Okay, so now I'm going to describe the contributions of our work. So as a first step we had to adapt LMDPs to allow for transition-dependent rewards. So I'm going to describe all of these in more detail in a minute. We then formulated a framework similar to MaxQ for hierarchical LMDPs. And we adapted something called inter-task learning to this new framework for hierarchical LMDPs. And finally, we ran experiments to validate this idea. So in the original LMDP formulation, the reward is just depends on the current state. But for our purposes, we need the reward to depend not just on the current state, but also the state that you transition to. So the reward now is a function from pairs of states. And actually, it's quite straightforward to adapt the math from the original paper to come up with the new value function in terms of z, and the value function in z is still linear. And even the optimal control can be easily obtained. And even better is that the update rules for z-learning and the importance sampling are exactly the same as before. We don't even have to modify them to account for this new model. Okay, so then what we're going to do is, instead of creating a hierarchy of MDPs, we're going to create a hierarchy of LMDPs. So we're going to assume that there's an underlying LMDP L. We're going to decompose that into a set of tasks with L0 as root. Each task is going to be its own LMDP. And probably the most limiting assumption that we make in our paper, for this to work, at least currently, is that for each state that I perform a task, that state always terminates in a unique state. But the unique termination state can be different depending on which state I apply the task. Okay, but the termination state is unique. The transitions of each task include some of the transitions from the original LMDPL and some that are due to subtasks, just as before. And just as before, the reward of a task decomposes in terms of the value functions of the subtasks. Okay, so again, we've done all of this math in the paper. Okay, so in hierarchical reinforcement learning, one way to speed up learning is if you have a series of tasks. For example, in our case, we have navigate tasks that navigate to different locations. And those tasks share transitions. Then you can make learning act faster if you use transitions that are sampled during the learning of one task to learn about the value function of other tasks at the same time. So this is called intra-task learning. You're learning about multiple tasks at once, even though you're only currently executing one task. Okay, so for MaxQ, this is easy because Q-learning is an off-policy algorithm, so you can easily sample using another policy and then apply Q-learning. But for LMDPs, there was no known off-policy algorithm. So our idea, so what turns out to work, is to apply the rule for importance sampling. So we're going to sample transitions from other tasks, and then we're going to learn now about the value function for task I. And what we're going to do is we're going to act as if we sampled, we're going to apply the correction term as if we sampled using the estimated policy of the current task. So this really seems wrong. And in fact, importance sampling in general is not going to work if you sample using different distributions every time. You have to sample using the same distribution, even though this distribution can be moving, as in the case of Z-learning. So why does this work? The correction term seems wrong here. Well, something that Todorov apparently didn't notice, if we plug the expression for this correction term into the update rule, it turns out that this update rule causes Z to move in the direction of the Bellman operators, which is exactly the target specified by the Bellman equation. So even though it looks like we're doing importance sampling, we're actually moving exactly in the direction that the Bellman equation tells us to move. Okay, so this allows us to learn much more efficiently in these hierarchies. Okay, so we ran two sets of experiments in relatively small domains, one called the taxi domain and another called an autonomous guided vehicle domain. Our main goal is to show that hierarchical MDPs allow for faster learning than hierarchical MDPs, or MaxQ. So we want to compare Z-learning with Q-learning, and to do that, we constructed artificially MDPs and LMDPs that have exactly the same value function. And we pre-computed the value function so that we knew what it was, so we can measure the error from the correct value function during learning. Also, we applied state abstraction during the experiment. So Dietrich, the original author of MaxQ, he suggested, or he showed that there are 5 different forms of state abstraction that are safe for MaxQ. And in fact, since we borrowed the MaxQ formulation, the same 5 types of state abstraction is also going to work in our case. So we apply those state abstraction by ignoring irrelevant state variables, for example. So these are results from the taxi domain. On the left-hand side is the learning of the low-level navigate tasks. On the right-hand side is the learning of the overall task. So we compare different versions of Q-learning with and without intra-task learning, and same for Z-learning, and also Z-learning with and without importance sampling. And it turns out Z-learning with importance sampling and intra-task learning significantly outperforms the other algorithms on this task. In the overall task, there's still an improvement, but not as clear. And you can see that Z-learning without without importance sampling performs really poorly, because doing a random walk is not going to cause you to learn very quickly. The story is roughly the same for the AGV domain. In the left-hand side are the low-level tasks. In the right, for the overall task, we run a different experiment. So in the AGV domain, the goal is to deliver some packages at the location. So we measure here the throughput, the number of packages that are delivered to the intended location. And in the right, so in the taxi domain, when we learn the high-level task, we assume that the value functions for the low-level task have already been learned in advance. But here we learned everything. We ran a hierarchical execution and learned about all the value functions in parallel. And also in this case, you can see that Z-learning with importance sampling is much more efficient than Q-learning. Okay, so in conclusion, we've presented a novel framework that combines max-Q decomposition and this idea of linearly solvable MDPs to form hierarchies of LMDPs. So, from the perspective of hierarchical reinforcement learning, we can take benefit from these properties that LMDPs enjoy, that principally that learning algorithms tend to be faster. And from the perspective of LMDPs, we address the curse of dimensionality by decomposing tasks into subtasks. And we've shown in experiments that hierarchical intra-task Z-learning outperforms the state-of-the-art methods for standard for hierarchical reinforcement learning. Okay, so this is
Questions?
It's possible I misunderstood something at the important sampling step, where you're talking about cross-learning for the importance of using one, we learn on one task to another. So the important sampling is based on the other task, but shouldn't it be a joint function of both the other task and this task? You know what I'm saying? Like learning to drive a truck helps you learn to drive a car, it doesn't help you learn to ride a bicycle. It's not a function of both tasks.
right. I mean, in general, the idea of intra-task learning is that the more examples of transitions you see, the faster you learn. Okay, so you take advantage of the fact that other tasks perform the same transitions that you might do if you were exploring. So the other issue here is this update rule. As I said, it appears to be the wrong correction, because you're correcting as if you were applying your own policy, whereas in fact you sampled using another policy. Because of the expression you get when you expand this update rule, it turns out to work. Anyway.
All right, any more questions? So I actually have a question. Because of the correction term, can you give us an intuition when the intra-test learning will not work?
So using this update rule is always going to work, because it always gives you an update in the direction of development error. So,
I mean, even for the regular pure learning, right? So if you have intra-test learning, sometimes it might change you not in the most optimal direction, right? So I guess what you're saying here, that's really the best thing you could do.
Okay, so in general, if you look at the Z-learning, so So this is what you want as a target for C. So you want it to be the sum of the probabilistic dependent P times something that depends on the reward you get and the Z value in the next state. So when you apply Z-learning, P doesn't appear. So implicitly, for Z-learning to work, to give you this, to push you in this direction, then P has to be the distribution used to sample these next states. Okay, so when you do importance sampling, you instead sample using another distribution. So then you have to account for this difference, and that's why you apply this correction term. And what we discovered is that applied this correction term has a secondary effect of actually moving you in the direction that you want to go. And that's part of the reason why learning is so much faster for the green line. I mean, Todorov had a similar graph in his paper where Z-learning with importance sampling was much faster, but I don't think he understood exactly why this worked so much better, which was what we discovered in this paper.
Thanks. More questions? So let's thanks the speaker again. This is a presenter for the last paper in the session. So, I think unfortunately they're not here. So let's take a break and we'll be back in 20 minutes. Thank you.